And finally, we have the hard-soft interaction principle, which is just another term for the HSAB theory, but it uses the word interaction because instead of limiting ourselves with the concept of acids and bases interacting with each other, the HSAB theory is in fact extendable to other kinds of reactions. That is why we have the hard soft interaction principle. Again, the concept is the same. You have hard and soft species. Okay, so let's start with something more relatable to us, which is ammonia and also pH 3. So you have nitrogen and phosphorus belonging in the same group with phosphorus a period lower than nitrogen. So you know that nitrogen is a weak base with a base dissociation constant of 1.8 times 10 raised to negative 5. And from what we you have learned so far at this stage, you know that with this Kb value, it's already considered a weak base. However, if we compare NH3 with pH 3, pH 3 on the other hand has a base dissociation constant that is in the magnitude of 10 raised to negative 26, which is way, way much smaller than 10 raised to negative 5. And in this comparison, we can say that ammonia is actually a strong base from the perspective of pH 3. So again, this can be explained using your HSAB theory, but again, we'll be using the hard-soft interaction principle. Okay, so with the Hsip, um, again, let's apply the species interacting with ammonia and pH 3 in this case is your hydrogen ion or your proton, which is a hard species. It's very small. It has a large or high charge density, +1 charge on a very small species. And ammonia, being a smaller molecule than your pH 3, can interact more favorably with the proton, with the hydrogen ion. And this makes ammonia a stronger base compared to pH 3. However, this will not be the case if our acid is a different species. For example, our acid is platinum 2 ion. In this case, platinum 2 is a very large cation with a charge of +2. So the charge is different by only 1 unit from that of the hydrogen ion, but the size difference would be much larger. So platinum 2 is considered a soft acid. So if our acid is platinum 2, then pH 3 would be the stronger base than NH3. So there would be stronger, more favorable interactions between platinum 2 ion and pH 3 molecule compared with ammonia molecule. So again, you see here, we are extending our perspective. We are not limited with just the proton donation, proton accepting, or the electron pair donation, electron pair accepting. We are extending because we are considering the charge of the species, the size of the species, the polarizability of the species, and also the electronegativity of the species. So again, the hard-soft interaction principle, this term is used. It's the same as the HSAB, but from my reference, it says that using this hard-soft interaction principle will give us this mindset that the theory applies to so many types of reactions and not just acid-base reactions. Now take note, this HSIP does not say that Lewis acids will not interact or soft Lewis acids will not interact with hard Lewis bases and the other way around. In fact, they will interact, but this is not the most favored type of interaction. So, for example, if you have a hydrogen ion, okay, okay, this one will explain why HF or hydrogen fluoride or hydrofluoric acid is a weak acid. Okay. Despite the fact that fluorine has a very high electronegativity. So H plus or hydrogen ion can potentially interact with either water or the fluoride ions in our system. So in this case, the unshared pair of electrons that you have on the fluoride ion and on the oxygen of the water molecule to which your proton binds are in orbitals of similar size. So because oxygen and fluorine are in the same period, so the electrons that will be used by oxygen to donate is found in a 2p orbital. And likewise, the electron pair from fluorine are also or is also located in a 2p orbital. In addition, okay, you have the fluoride ion having a negative charge, and this makes it more attractive for the hydrogen ion. And with these factors, we can say that the hydrogen ion bonds preferentially to the fluoride ions instead of the water molecule, which means that um, the reverse of this reaction is stronger than the forward. Means that the interaction of HF between the hydrogen ion and the fluoride ion is preferred rather than the interaction of the hydrogen ion with the water molecule forming the hydronium ion. And this explains why HF is a weak acid and not a strong acid in comparison with the rest of your hydrogen halides. So if we consider a similar situation with that of chloride ions, this time the lone pair of electrons that will be donated by the chloride ion is located in a different orbital. It's in a 3p orbital. Okay. And this means that the binding of the hydrogen ion with the chloride ion is that not much favorable because of this difference in the size of the molecular orbitals. And this makes your hydrogen ions prefer interaction with the water molecule. So, because in terms of size, it's nearer. So, a hydrogen ion will have a preferential binding with the water molecule, and this means that you have this reaction, which is essentially complete. And this makes hydrochloric acid a strong acid. And that's the end of this series of lesson about your Lewis acids and bases and also your Hsab or the Hsip.